All right, so this morning, polarization to set you up for Kurt's radiative transfer lectures. And so, as I say, at least an hour's worth of polarization. So we'll see where it goes in the sky and the water. So the idea is polarization is important. We've been measuring irradiance and radiance, and polarization of the light field is another parameter we can measure that could give us additional information. Or it can also be a problem in your measurement if your instrument is polarization sensitive. If the light field is polarized, which like skylight will be, and water and light in the ocean will be, then you could be getting a measurement error because you're not taking this into account. So basically, the simplest light field we'll start with is a plane wave, and you can describe it in terms of a electric field along the L direction and electric field along the R direction. Here's the coordinate system with the light propagating in this direction. And remember that light's a transverse wave, so the oscillations are occurring perpendicular to where it's moving. If you describe it this way, we can't really tell what this delta is or that delta is, but what we can look at is the difference between the two, so one relative to the other. So if you look at these equations, what happens if delta, the difference is zero, if they're both the same? What's going to happen to these electric fields? In terms of, what were we left with? We're left with AL cosine omega t minus kz, AR cosine omega t minus kz. As time goes on in one spot, so we'll say z equals 0, as time goes on, what's going to happen to the amplitude in the L and the R directions?
Constructive interference.
Constructive, but they're in different directions. You can't get interference between the waves when they're polarized perpendicular to each other. So if we look, at time t equals 0, this is going to be a maximum and that's going to be a maximum too, right? At a time when omega t is equal to pi, what's going to happen? So if we're targeting z equals 0, so we forget all about these ones. So omega times t is equal to pi. What's going to happen? What's this going to be? What's cosine of pi? Negative 1. So this will be minus AL, and this one will be minus AR, right? So what we're talking about then is if I look at these coordinates, and I've got L in this way and R in that way, if there's delta R and delta L are the same, so there's no difference, then you're going to have something that at time t equals 0, we said was up here. At time t, omega t equal to pi, it's down here. So you have something that the electric field is oscillating back and forth along that direction, right? Okay? So that means the light's polarized in this direction, linearly polarized in this direction. If I have AR, say, equal to 0, what's the electric field going to be doing? So I have no amplitude along the R direction. And so that means that the electric field is always going to be going like that, right? There's no component on the R direction, so that's linearly polarized along this plane. Similarly, if we have a L equals 0, then it's going to be doing like linearly polarized like that. What happens if we have delta equal to pi over 2? All right? So let's see. So we'll say delta, so we'll have delta 0 here, and this is pi over 2. And we're looking at one position, well, z equals 0. So at time t equals 0, if this is 0, this is 0, that's 0, then what's the amplitude of at AL? It's just or at EL, it's just AL, whatever AL is. Let's make AL and AR equal to each other. So time t equals 0, this one is 0, so it becomes AL. What's this one become? Okay, it's 0, 0, pi over 2. So what's cosine of pi over 2? 0, okay? So basically at that moment in time, we have this, the electric field's all along the EL direction. So we have, it's looking along like that, all right? Now let's go to time omega t equal to pi over 2, right? So now we have pi over 2 here, we have 0, 0. So I have cosine of pi over 2, what's that? 0, okay? Come down here, this is pi over 2, this is pi over 2, this is 0 still. So I have pi over 2 plus pi over 2, pi. So what's cosine of pi? Negative 1, so you have negative r. So at that point, a little bit later in time, now the electric field is moved into where it's in this direction. Okay? And then you keep going. If we go to pi, so omega t equal to pi, this is cosine of pi, which is minus 1 again. So that's minus AL. This one is pi plus pi over 2, so it's 3 pi over 2. Cosine is 0. So now it's in the minus L direction, so it's here. So you have an electric field as time goes on is sort of rotating around in a circle. Okay? And so if you look at the tip of the electric field, it's going to be something that's oscillating around like that, or maybe the other way. Let's see. If I stand in one spot, stand in one spot, it went this way, and then this way, and then that way. All right? So that's called circular polarization, if it's rotating around there. And I could set it up so that instead of pi over 2, with a different phase shift, I can set it up so it's going the other direction. So one direction is called right circularly polarized. The other direction is left circularly polarized. Now, one convention, the light is traveling, in this case, the light's traveling out at you. So if I look down at the light, now Kurt, make sure I do this right. Well, the bad part with circular polarization is I can say, Kurt, make sure I do it right. What I'm really saying is, Kurt, make sure I stay consistent with what you want, because everybody flips it back and forth, okay? So, okay, so I look down here, and this is going to be right circularly polarized because it's going clockwise while I look down at the beam coming at me. If it was going counterclockwise coming at me, it'd be left circularly polarized. But you have to figure out what convention you want to use and stay consistent with it. But if you're reading it. So that's right circularly polarized, left circularly polarized, looking at the beam. This is all linearly polarized. In general, light would be what we call elliptically polarized. If you have polarization, the most general case is a combination of some circularly polarized light and linearly polarized light, so that if you look at the electric field vector, so here's our L and here's our R, as time goes on, the tip of the electric field vector could go like this and rotate around. Okay, so this is a combination of some right circularly polarized light and some linearly polarized light along that direction. All right, everybody see how that works? So the polarization is basically describing how the tip of the electric field is changing over time. So that's polarization there. Now, in general, we can't, the frequency of light, the wavelength, the light, from one of the things we taught, we said that the wavelength times the frequency is equal to the speed of light. That's true for every waves, right? The speed times the frequency is this. The wavelength times the frequency is the speed. So if the wavelength of light that we're dealing with is on the order of 500 nanometers or so, half a micron, the frequency ends up being really high, on the order of 10 to the 14th hertz. So we really don't pay attention and don't try to measure individual waves like that. what we try to do is measure intensities, although intensity the wrong term for what we've been saying, but magnitudes of the light field, if you want to call the flux. And also the light field is not just a single plane wave, but it's a superposition of many waves in general. So we have to have some more convenient description for it. And so what we use is a Stokes vector. And the Stokes vector has 4 elements into it. The first one is just the total radiance or intensity. I'm going to say intensity because that's sort of what I'm used to when I look at this, but it's the total radiance, say. The next Stokes vector tells you how much light is linearly polarized along this plane minus the amount of light that's polarized along that plane. So if we look, if light is unpolarized, then there'd be if you put a polarizer here, do you remember what happens if you look at light through a polarizer? So here's light, here's a polarizer, remember these things? And I'll stick it up here. I wonder why it's purple. Okay, so anyway, you see, everybody can see that? So we get light being transmitted through it, but it's been decreased. Unpolarized light. Oh, look at that. Wow, you learn something new every day. That is cool. So if it had been white light, it would just knocked it down by half. It was unpolarized. Obviously, this is polarized with the different colors. Yeah, that is nice.
They must have an LED projector with RGB, but they're putting out different polarization.
Yeah.
They're oriented differently.
Yeah.
Probably they never thought of it, that'd be my guess.
Yeah. They're really nice.
LEDs in there.
Yeah, I was going to show you, at some point I was going to tell you something else I'd tell my class about polarization, and maybe I'll do it in a second here. But that is neat. I've never looked at that. If we had one way you do stereo projections, or if you want to look at a stereo movie, is you would have two video cameras or video projectors, one polarized this way, one polarized the other way. And then you would have your eyeglasses are polarized one direction or the other, so that would present the two different pictures for you to look at. That's neat. Okay, so, but you see, light gets through here. So if I'm unpolarized, if this was unpolarized, which I totally expected it to be, when it came to here, you would see half the light blocked out. If I rotate it, because it's unpolarized, remember the polarizer doesn't matter when I rotate it. So you'd see half the light that way. And so if I make my measurement here, for Q, I'd get half here, minus half there, I'd get 0. Okay, so unpolarized light gives you a Q equals 0. U is polarized along 45 degrees minus polarized along the other 45 degrees like this. Okay, so in terms of my picture, this would be basically U equal to 1 because it's along that plane versus minus 1 would be along that plane. And then V is the leftover right circularly polarized minus left circularly polarized. So we have two linear polarization terms and then a circular polarization term. And with that, the Stokes vector, you can completely describe the polarization of the light field, of a light beam coming at you. And actually, and also the radiance. So you get, it's the complete description of what's going on for the light field coming at you. Some simple Stokes vectors. Unpolarized light is here. I 0, 0. Q is equal to 0 because there's as much. If you put a polarizer here, you'd see as much in one direction as the other. So that's 0, that's 0. Same thing, if you had a right circularly polarized analyzer or a left circularly polarized analyzer, you get 0, the same in either one, so you get 0. So unpolarized light looks like that. It only has a radiance or an intensity. Polarized along the L axis would be I, or I and I an equal amount here, and then 0, 0. Polarized along R would be I minus I, 0, 0. And then right circular polarized light, I, 0, 0, I. Okay, so basically that's the Stokes vector. Four component vector totally describes the polarization. Let me, while I'm, because it's sort of cool, and it doesn't really have anything to do with polarization in the ocean, but it's cool anyway. How many people have an iPad? Not that many. What do you guys have, the alternate ones? You got to have some sort of a thing like this. Okay, so I have my iPad. I'm on my boat. I have one of the early generations. The only reason I even have one is my wife's was stolen, and she got a new one. And then, believe it or not, the Charleston police called us up, and they'd gotten it back. And so we got sent. So I got one because I got her one that was stolen. So if you look at the iPad, I've got this iPad. I've got my polarized sunglasses. I'm sitting on my boat. I want to read the book, and obviously outside in the sun. So I'm going to be wearing my sunglasses. So I go and I, push the on button to try to read, to turn it on so I could get my password in. You know how they work, right? Even if you don't have one, you know how they work. So I have it, and I go to try to read it with my polarized sunglasses. Here's the polarizer. Oh, shoot, I need some glare. Okay, so it's dark here. So which way does that say the polarization of this thing is? So it's polarized like that, right? And I'm blocking the glare off the surface. So this is the way your sunglasses are going to be, right? So now I've got my sunglasses on. I'm looking the way I would want to read a book. I don't know about how you would hold this thing to read a book, but this is the way I want to read my book. And I put my looked through my polarized sunglasses. What do I see? Totally dark. Took me a while. I was sitting there looking at it going, oh, shoot, it's not working. The battery must be dead or something. And finally, I rotated it. So Apple, in their wisdom, in the first couple generations, decided that I should read my book outside this way and not this way. I was in class, and I only have this. What's that?
Why do they polarize the screen? Is it because of reflection?
Why is this thing polarized?
Why is that?
The iPad's polarized because that's how these things work. Is the light comes in through a polarizer, the liquid crystal rotates the polarization, comes out, and so the light, what you're seeing basically is the light having come in, been polarized. If it's rotated properly, it comes out and shows you something. If it isn't, it's dark. So that's basically a liquid crystal display. Light comes in. So the last thing it sees is a polarizer, and the first thing it sees is a polarizer.
But when you say light's coming in, it's coming in from the back. It's not coming in from the sun.
Well, some of the reflective ones were that way. This one probably, the last thing you see is a polarizer. Okay, and so, yes, ma'am.
Just a question, those anti-spy screens on your phones, are they polarizers too?
I think they are, but I don't. Yeah, they are. Okay, yeah.
I had an iPhone that
Yeah.
I read with my polarized sunglasses
Yeah.
on, and I cracked the screen.
Yeah.
And when they replaced the screen, I had to read it sideways. And then crack the screen again, and the new screen that they put on was very cool.
Yeah. So I didn't have I was giving this lecture about light and physics, and I didn't have my iPad with me, and so I'm standing in front of 150 students, and I don't have my iPad, and I say, okay, well, one of you have an iPad, right? And so they gave me an iPad. But of course, they're students at University of Miami. They have more money than I have, and so they had a new generation one. It turns out Apple fixed it. They figured out what was going on. So I went to do it, and it was like, oh, shoot, nothing happens. Anyway, it had nothing to do with the ocean, but it's sort of cute. Okay, so we have this. Now, okay, so here's a slide I couldn't figure out where to put, but I need to get a few definitions in here. The coordinate system that I'm going to use for polarization, because I'm concerned with polarization in the light field above me, is I have to have some way to describe what is the L plane and what's the R plane. And so my coordinate system is For light coming, I have the experimental side, so I'm worried about light coming at me. So I have light coming at me sitting here, my camera is sitting here, propagating from some direction. The L vector is in the plane that contains the zenith and the direction I'm looking at, and the R direction is perpendicular to that. Okay, everybody sort of see how that works? And then, so that's the polarization plane, coordinate system I'm going to use. There's a few terms. There's degree of polarization. If you look at it, it's q squared u squared plus v squared over I. Basically, it's telling you how polarized the light is. And it ranges from 0 for unpolarized light to 1 if it was completely polarized. Okay, so when I say degree of polarization, I mean that. When I say degree of linear polarization, I just mean q squared plus u squared divided by I, because I'm not concerned about the circular polarization then. In general, the light field in the ocean and the atmosphere is very little circular polarization. So usually you can just consider linear polarization. The plane of polarization, chi, is basically telling you if it's linear polarization where the polarization is occurring. And just for completeness, I'm not really going to talk about it, but the ellipticity tells you how much circular polarization you have of your polarization. Okay? So those are some terms. I don't think I talk about ellipticity at all, but I do degree of polarization and plane of polarization. So we have this nice Stokes vectors. For a column vector orientation, nicely set up. Scattering processes have linear transformations of that Stokes vectors. So I can get a 4x4 matrix and describe how this thing transforms the incoming light to the outgoing light. And I do it the opposite of Kurt. And I guess everything I'm doing is the opposite of Kurt. I put my primes on outgoing and my unprime on the incoming. But anyway, remember how to do matrix multiplication? Anybody not remember how to do matrix multiplication? Good. Well, okay, one person. So basically I have that element. If we look at this element, it's I times this one, Q times that one, or I times this one plus Q times that one plus U times that one plus V times that one. Gives me that one. This one would be I times this, Q times this, U times that, and V times that. Okay, so there's matrix multiplication. So if I know this Mueller matrix, I can, for some scattering system, I can completely describe how any incoming polarization state's going to leave. Okay, so it's like everything you want to know about a scattering. And if you have unpolarized light coming in, remember, it's be I 0, 0, 0. Outgoing, you look what's going to happen. The I component, the radiance you get out coming out, or the intensity, would be M11 times that element. So this is the phase function, scattering phase function that we've been talking about, this one element. But there's really 15 other elements, roughly, that are involved in scattering. Yes?
So you're saying that if you know how the light comes in, like what its polarization is, and then multiply it by, I guess there's still
This Mueller matrix.
about its scattering properties?
If you, wait, excuse me, say that.
I'm asking, yeah, so is the Mueller matrix about like the scattering?
The 1-1 element, the Mueller matrix describes how light is transformed in some sort of a linear process. It can describe, I'll show you in a second how it describes what happens when light goes through a polarizer. If you're talking about a scattering system, M11 is your volume scattering function. The rest of the elements tell you how polarization is changed or affects the scattering.
So are those known for?
Well, I'll get into that. So basically, your me codes, I don't know if the me code that he gave you, it would give you the matrix elements for, it didn't? Okay, well you can get the matrix elements through me codes for scattering from spheres stuff. We'll talk, but that's what a lot of this talk's going to be about. Okay, everybody clear on that? So 4x4 example. This is the Mueller matrix for a polarizer, where theta is describing the angle, acceptance angle of the polarizer. We look, if I have this polarizer, so basically we're saying theta is equal to 0. So I get a 1 element here for that element. I get a 0 here because sine of 0 is 0. These are all zeros. These are all zeros. This one is 0 because sine of 2, 0 is 0 still. That one's 0. This one's 0. So I only have, for a linear polarizer, set up so its acceptance is along the L coordinate. It looks like this. So like any light coming in, I, Q, U, and V, no matter what it is, you multiply it by this, and what you're going to get is, why is this half here?
Because when you're fully off, you get half pass.
If it's unpolarized and it goes through here, you would just have 1, 0, 0, 0. You get 1 up here. And so your intensities drop by a half. Okay, so that's the half. So anyway, so whatever comes in, multiply by half, you get I plus Q 0 times a half. So it's I plus Q over 2, and then 1, 1, 0, 0, which we said before was light polarized along the L coordinate. Okay, so linear polarizer works really well. 2 crossed polarizers. What am I going to see out of that? I take 2 polarizers, I cross them. Even if that's sort of cool. I still like that. Okay, but see what happens in the middle? It's all dark, right? 2 cross polarizers, I get dark. So let's see what happens in the Mueller matrix. We have our other one that we had before. We have one that's now along the R direction, that's -1 and -1. We multiply it all out. This one would give us I, 0, 0. You multiply it by this Mueller matrix, and you have the top element is I times minus I. So, well, I times 1 plus I times -1. 1 minus 1 is 0. So we get 0. We get no light out of it. Works perfect. Okay? So there's 2 cross polarizers. Now, what happens if I take a third polarizer and I stick it in at 45 degrees between these 2 polarizers? How much light do I get out? Do I get any light out? Okay, let's see what happens. Can you see that? So by putting a polarizer in at 45 degrees, I now get light through. You can think of it as the light from the first polarizer, say, is polarized this way. Now the polarizer at 45 degrees, it's going to let light through, half the light through, because half of the light's polarized along this direction. So it's going to go there. And then I knew the next polarizer like this, there's a half of that component that's along this direction. So I get light through. By putting a polarizer in between, I can get light through. What happens if I line it up with one or the other polarizers? So I have it like this. Now if I line this one up, say with either the front polarizer or the back polarizer.
No transmission.
What's that?
No transmission.
No transmission. Why?
Because it's not adding an additional rotation.
It's not adding a different additional rotation. It's going to be lined up with one or the other. It's not going to really do anything in the process. So we look, 2 cross polarizers with another one in between at 45 degrees. That's this Mueller matrix. And you could work through it. You get 1/8 of the light. Let's see. Yeah, you continue it out. You get 1/8 of the light. And now but that light's polarized along the direction of the last polarizer that you went through. So there's sort of how Mueller matrices work. Circular polarizer. To make a circular polarizer, what I have to, from unpolarized light, I have to have a polarizer at 45 degrees, say, and then what's called a quarter wave plate. A quarter wave plate has a retardation that when light goes through one axis is a quarter wave, so 90 degrees out of phase with the other axis. Okay, so as light, it's basically one along this direction, light's going to end up going a little bit slower or faster than on this coordinate. So when you get out, they're now out of phase with each other by 90 degrees, which is our pi over 2 that we had, so it becomes circular polarized. And so if you do this, you end up with circular polarized light at the end. So these matrices all work pretty well. So now the trick is to determine the Stokes vector, I have to have it's a 4-element thing. I have to have 4 independent measurements to try to get all 4 elements. Okay, so I have to somehow do that for the Stokes vector. To get the Mueller matrix, there's 16 elements. So I need to have 16 different measurements where I put in different polarization states and I measure different polarization states of the output. And if I carefully choose my 16 measurements, then I can determine each of these Mueller matrix elements. Okay? So and that's basically what people started doing is you'd set up with a whole bunch of polarizers systems to start with, vary I, Q, U, and V, and then measure the polarization of the light coming out with a bunch of other polarizers and combine them algebraically, and you'd get the Mueller matrix. And in a lot of what I'm going to show now, I normalize all the other elements to M11 so that the Mueller matrix has 1 here, and everything else shows you the polarization states, because it's easier to separate the polarization from the volume scattering function. Okay, everybody clear so far? Okay, so instruments to measure the Stokes vectors of the light are basically variations on radiance measurement instruments. If you remember, I talked about those the other day. You can either have like 4 Gershon tubes with different polarizers in front of it, 3 different polarizer this way, a polarizer that way, and a polarizer that way, and then a right circular or left circular polarized analyzer. Usually people would just do 3 because there's very little circular and it's a waste of money to deal with that one. So they have 3 different Gershon tube radiometers with these different polarizations, and you can combine them to get the Stokes vectors. Or if you have an imaging device like a fisheye camera, you put polarizers in those, and you can get the same. You need 3 images with the fisheye, or 3 different fisheyes with different polarizers to get the linear polarization state. So here's an example sky instrument. And it's got a fisheye lens, sort of relayless system, polarizers up here, interference filter to choose what wavelength I'm going to look at, and then some sort of a camera system, CCD, down here. By switching in this filter wheel of polarizers, and I take 3 images quickly in a row, I can get the sky's radiance distribution, polarized radiance distribution. Okay, so the Stokes vector is for all the different directions. So that's one example for the sky. And here's a picture of that thing roughly, or of another version of it, on the edge of an end of an arm off a flip. Anybody not know what flip is? Research vessel flip? Okay. Flip is the coolest vessel or platform. It's basically like 100 meters long, somewhere around 100 meters long. And it has a bow section with living quarters, and the rest is a long tube. And so they tow it out to where it needs to be. It doesn't have motors. And they flood this part of it, and the whole thing goes up like this and becomes a spar buoy. And so you've got this thing with like 3 or 4 levels up here that you live on, and it's this huge buoy that you can work on and do measurements off of. It's very relatively stable. It doesn't go like this much. It just goes up like that. And so it's pretty cool for things. Obviously, it must well, the camera or somebody must be tilted a little bit. Anyway, this was an arm sticking out from it during an experiment we were doing, and there's the sky camera on it. Another picture of it. Okay, so you have to have, on a ship or a moving platform, you have to have stabilization. So that one had this system they use from helicopters to try to keep a film camera stable. In the water, the problem is with wave focusing and stuff, you can't depend on the light field being stable enough. So you have to somehow do it simultaneous measurements. So one way to do it, if you look down here, there's 4 Gershon tubes, radiometers. Basically, there are 4 of the LU sensors that we have in class on the Hyper Pro, but with polarizers in front of them. And then there's this is Alex Gillerson's the group at City College, New York. Basically, it had a stepper motor. It's got propellers to move it into different directions, so you can look at different directions with it. The nice thing is it's hyperspectral, so you get the polarization properties at all wavelengths. So that's one way to do it. Or you take a collection. This is POLRADs. Basically, it's 3. This is sitting on a wood platform on the deck, but it's 3 different cameras, fisheye camera systems with polarizers in each of them, so I can take simultaneous images. Or here's a different version, which has basically 4 different. I did measure circular with this, so it's 4 different fisheye cameras with fiber optic bundles. You know, like you use, not you use. You're all too young. If you have a colonoscopy, which you haven't had to have yet, but some of us have had to have because you get over a certain age and the doctor keeps bugging you. Anyway, fortunately, the colonoscopy, I think it's not this big. It's about that big. But each of these fish eyes are focused onto a coherent fiber optic bundle. They come around, and there's a set of 4 of them here that are all imaged onto a camera. So in one image, I get 4 different polarization states with this system. So those are 2 ways you can do it with fisheye lenses. You want to say what Riley's new project is going to be? You want to say what yours is, or you want me to just say it? Or?
I can say it quickly. So instead of having 4 separate sensors, each with a different polarizer, we have one sensor, but each pixel on that sensor has a different unique polarizer on each one. So you get a 4x4 matrix array across all the pixels of a linear polarizer. So they're side by side. It's kind of unique, and you can take one picture and get the degree of linear polarization from that.
The neat thing is that there were some, years ago, there were some one-off systems. There was a guy at Washington University in St. Louis who had one. Now Sony makes the chip commercially, so you can just buy one from the company we're using is FLIR, which used to be Point Grey. Anyway, nice little teeny camera that does it. So that's going to be the next generation. I can't show you a picture because I don't have a picture of it yet, but that's what we're doing now.
Jim, what did you use for the domes over this?
They're glass.
They're glass.
They're all glass, yeah. They're all glass, and I should look through cross polarizers to make sure that they're not stressed in some way. But they're glass. So one of the more expensive parts, well, you'll notice if you get to build your own instruments, it's stupid, but the most expensive things are usually the housing, and then the windows in this case were pretty expensive. They had to be ground out. Okay, so that's how you have to measure the Stokes vector. To measure the Mueller matrix, I said before, you have to have 16 different elements, so you have to have 16 separate measurements to be able to do it. One way, which was my thesis stuff, it's sort of embarrassing, I guess, probably, 30, I graduated in 84, so what's that, 35 years?
I'm 24 plus 10, so.
Yeah, okay, 35 years. So 35, I'm still showing pictures for my thesis. This is back before you had computers, the dark ages, when I had to, when I had to draw it with a Leroy set, all the figures and the, you probably like ink and pen drawing. So this was drawn by hand because there was no computer. I couldn't draw computer graphics. So this is done by hand. I had this lab, so I'm sorry I get into all these stories, but I had a lab that was basically a closet they had given me in the physics department that was the air conditioning handling room effectively, so it was louder than anything. So I'm sitting there drawing one of the pictures for my thesis, one of these things, I'm almost done with it, and I'm sitting down concentrating, and my girlfriend, my wife now, walks in, and it's so loud I don't know if she's there. So I'm sitting working on it, and she says something that startles me. The pen goes all the way across, ruins that whole drawing. Anyway, but the point of here is the way the system was set up, there were electro-optic modulators that rapidly changed the polarization state of the light. And so there were 2 of them in the input, 2 in the output. And so basically by looking at different frequencies of the exiting intensity, you could get the different polarization the different Mueller matrix elements. So it's probably the most sophisticated instrument to do this that's been built and has ever been used. So here's what the Mueller matrix looks like for Rayleigh scattering, and I'm normalized, so it's 1 up here. Remember our lab experiment? At 90 degrees scattering from the water, what was the what was the thing about polarization of the 90 degree scattering? Do you remember? It was maximized, and then it was along which, if you're coming in like this and you're looking from where you are, which way was the polarization set up? Vertically, okay. So if I have unpolarized light coming in here, so 1, 0, 0, 0, I throw it in here, I get a 1 here, I get a -1 here at 90 degrees, and then I get 0, 0. These are actually zeros, you can't see, but those are 0. So I'd have 1, -1, 0, 0, which is fully polarized along one direction, okay? Perpendicular to the scattering plane. So that's that part of the matrix. Most all these off-diagonal elements are 0. You have the circular or the 45 degrees, and the circular polarization are set up that in the forward direction, you basically get no change. In the backward direction, it would take right circular and make it into left circular polarized light. Okay? So this is what a Rayleigh Mueller matrix looks like. Low index particles also scatter that way through the Rayleigh-Ganz approximation. This is what I just showed you. So m equals 0. Forward scattered light, you have 1. This is 0, 0, 1, 1, and this one you can't see is 1. So you have 1, 1, 1, 1. If you remember what that is in matrices, it's the identity matrix, so it doesn't change in the forward direction. At 90 degrees, we saw this is -1, that's -1. In the backward direction, these are zeros, this is -1, and that's -1. So backscattering gives you -1, flips the U and flips the V element, but doesn't change the Q and the U. Okay, so that's sort of what those do. Here is the Stokes vector for, it's a degree of polarization for the skylight, a perfect skylight with Rayleigh scattering. What you see if you put the sun here, this purple corresponds to 0 degree of polarization. Remember when we looked around with our polarizer at the sky, that you would see, we saw the maximum polarization, 90 degree scattering angle. Remember that? If you look toward the sun, not at the sun, but closer to the sun, you would see very little polarization. And this is that band of very high polarization. A perfect Rayleigh scattering would have a full 100% polarized in that direction. Single scattering. The Q and the U elements look like this. Q over I and U over I looks something like this. Q is flipped over, is symmetric on the other coordinate. Here I'm looking, this is straight up. This is the horizon, and as I rotate around it, azimuth, this is toward the sun. This is away from the sun. So the sun's over here. Over here is looking that way. Over here is looking that way. Okay, that's sort of the thing. This is symmetric. This one is anti-symmetric. Everything purple up here would be orange down on this side. Okay, but that gives you a sort of a view of what it looks like for a perfect, easy single scattering situation. Here's an example for in-water upwelling data. This is Q and U, and look, it's pretty similar picture to what it was for the sky. This is clear water, and so if you look, it's sort of the same. The sun in this then would be, well, this is backscattering. No, wait. Let's see, which way is it? We'll go back over here to this picture. So with this picture, this is toward the sun, and I've got that big purple area there. And so when I look back here, this has got to be looking, the sun's over here coming in, and I'm looking off that direction is where that is, okay? Pretty sure. Might be backwards there. I should have looked at that closer. But anyway, so there's sort of a picture of what Q and U look like for the Stokes vectors. As I said, there's very little V, so I don't have V shown. In fact, I don't think I even. The only place in the ocean you get really circular polarization, in general, is in the natural light field, is when you're looking at grazing angles from the surface. So you're looking outside the Snell's cone at light coming up and reflecting back down. Then that light will come in with a little bit of circular polarization right near the surface. In general, there isn't anything else. So that I showed you Rayleigh. This is what seawater looks like. An average of the seawater for ocean water based on measurements in the Gulf of Mexico, the Atlantic Ocean off of New York, Pacific Ocean off Monterey, and several other cruises. Basically, remember the Rayleigh Mueller matrix went to -1 here. It doesn't quite go to -1. Similarly, this went to -1, 3, 3, and 4, 4. It doesn't quite go to -1. The 2, 2 element is 1 for Rayleigh. For real ocean water, it tends to drop. This element is indicative of non-spherical particles. So if you have spherical particles, this has to be 1. When you start getting non-spherical particles, this deviates from 1. So it sort of shows that the phytoplankton that I was measuring here, or whatever was in the water, basically is non-spherical. Okay, so the deviation there. And you can actually relate the fact that this is no longer 1 to part of why these don't go to -1 too. So there's ocean water. This is now the degree of polarization and the plane of polarization. This is the anti-solar point is up in there. This is the 90-degree scattering in the water where it's more highly polarized. It sort of has these points that have 0 degree of polarization. They're called neutral points. It's sort of interesting that they're split in clear water like that. Okay, so why do you care? So why would you care? The one thing people keep rediscovering, I don't know why, is that you can use polarization to help you look in the water farther. Because the scattered light will have some, if you have light that you start with polarized, and you remember the Rayleigh scattering element, and if you look at this, if I start with light polarized, say circular polarized in one direction, when light is scattered back to me from particles in the water, it'll come, if I start with right, it'll come back at me mostly left, circularly polarized. So, but in general, the light reflected from a target will be unpolarized coming back. So if I put a discriminator on there and eliminate the left circular polarized light, I can eliminate a lot of the light that's been reflected in the path. So you can enhance visibility with that. Gary Gilbert talked about it in 1967, yet you keep seeing papers talking about it coming out and doing it over and saying, oh, look what we found. We can enhance our transmission. Anyway, but now you guys know, so you don't need to discover it again. So there's that. Animals use polarized detection and polarized light for camouflage. There was a big Navy project. You were involved, weren't you, Kurt? Oh, okay. George Cadwar was. Molly Cummings, University of Texas, Austin. Roger Hanlon at the Marine Biology Lab. He's done a lot of work on polarization and how animals use polarization, both for camouflage and for signaling and such. There's
There's about 21 different groups that have polarized vision.
Okay.
Their eyes are different than ours. They sense polarization.
There's some of the animals that actually can vary the polarization of the reflectance from them to try to hide or not hide or signal, or it's pretty interesting, the things.
Cephalopods have polarized vision.
So it's anyway, depolarization due to minerals, remote sensing applications, Volton, I believe this, yeah, Volton measured different silts, and as opposed to what I had for, I showed you for the 1-2 element of the Mueller matrix, he ends up with something, this is minus, so you got to flip it over my diagrams. But you can see things that have a maximum at different angles. So the idea was that you should be able to tell by looking at the remote sensing signal, you could tell these different properties of the particles in the water. Probably the most likely thing you'd be able to tell is by looking at the degree of polarization in certain directions. You can get a value for the beam attenuation divided by the absorption, okay? Why, from what we've talked about, why would that be sort of an interesting parameter for being able to get that from a remote sensing signal? Can we get absorption from a remote sensing signal? Yeah, right, it's pretty related to the reflectance. What else can we get from remote sensing that we know about so far? What's that? Backscattering. So we can get backscattering for the remote sensing signal. Do we get forward scattering? No, it's not really very sensitive to the forward scattering. And so you can't, and remember the beam attenuation in the ocean is pretty much dominated by the forward scattering part, not the backscattering part. And so we don't really have a way to get the forward scattering component, to get the beam attenuation. And so the idea here is by looking at the degree of polarization in certain angles, you'll be able to get the C over A ratio. You already have A from other ways, so it could give us some signal that we can't otherwise get. All right, so that's probably, in my view, that's the most likely thing you could get out of polarization. But it's an open field. There's still there has not been that many measurements done, so we can do other things.
There's one paper using polder, and you mentioned that, where people could see the Amazon, the inorganic particle in the Amazon is increasing backscattering ratio. I mean, in a sense, increasing. They sense the degree of the increase in the degree of linear polarization as they move towards waters with more inorganic particles.
So if you look at this, the 1-2 and 1-2 elements are, remember in the Voss and Fry thing I showed you, the values were about 0.6. If we did a bunch of samples of phytoplankton, low index particles, they're all up in here. If you notice this with the silt, it drops it down. So the degree of polarization will be less in a case that you have more mineral dominated was the area. Now the polar people I heard go both ways at times. So
There's a publication.
yeah.
But there will be two polarized
Right.
So
So-
this is information we have no access as a field before.
Mhm.
And that would be room for amazing exploration and trying to get more information about particles than we have just with scalar today.
Mhm.
So this is a very hot, it will be a very hot field. There's a few people that do it, but it will become much hotter for young scientists to get
Yeah.
into.
One thing disappointing in the ocean, is that because they're low, the particles, the phytoplankton are fairly low index. In general, the Mueller matrix is close, like I showed the average, it's close to a Rayleigh type in general. In the measurements I made of the Mueller matrix, in all the places, there was only one sample that really was clearly different, and that was a sample taken near the bottom of the New York Bight. Everything else was pretty much regularly in there. I didn't show, I have in the paper the uncertainty or the error bars based on, I also list my uncertainty in there. Okay, so I did do that correctly, but I also have what the variation was in my average, so you can see how tight that was, and it's not bad. But there enough weird situations occur which do have a different Mueller matrix. So as Manuel says, there's two polarimeters. The reason in the ocean, I think it's because they're very low index particles and they follow closer to Rayleigh-Gans type approximation. In the atmosphere, you have a much larger difference in the refractive index between the particles and the medium. And so the atmosphere, aerosols and stuff have very good, interesting polarization properties. And so a lot of the polarimeters are mainly driven to help with atmospheric correction and help in characterizing the atmosphere aerosols. But they're on there, we're gonna get a signal. We should look to see what else we can get out of it. Because you think atmospheric correction is hard for just getting the radiance correct. Wait till you try to do it and try to look at the polarization properties of the ocean from the top of the atmosphere. That'll be cool. Okay, the other thing is your instruments may have polarization sensitivity. Spectrometers always do if they don't have scrambling of some sort. RSR. Yeah, so older remote sensing reflectance measurements from above the surface. That's above the surface measurements. You're looking at the surface, light reflected off the surface. That's going to be really polarized. So if your instruments, the older ones, didn't pay attention to it, that's a problem. You need to make sure that your above water instruments are either not polarization sensitive, or Sinbad, a bunch of people here, I've heard Sinbad mentioned a bunch of times from people in here. That's a French instrument that is set up to look at polarization. You have to take into account polarization when you're using that instrument. Satellite instruments are polarized to greater or lesser extent, so you have to take that into account, their polarization sensitivity when they're working with their data. They try to get it to less than 2% in the blue. VIIRS, the second VIIRS, the one on J2 it's called, ended up out of spec on its polarization sensitivity. It had a polarization sensitivity in the blue of more like 4 or 5. It's because they tried to correct one thing that was wrong with the first instrument, and when they corrected that, they ended up introducing polarization sensitivity. So they have to take that into account. This is an old slide, I'm sorry, I didn't notice. There was going to be a polarimeter on this instrument called Glory. Unfortunately, Glory decided not to sample remotely, but sample in situ, and crashed into the water and didn't launch properly. But the new sensors are being developed. There's 2 on pace. It says trying for 1. They're going to be 2. Yeah, so that's it. Either I didn't pay attention, or I was clear, or you didn't ask as many questions this time. Any questions? Yeah.